Hello, pre-calc. Are you ready? We're going to talk about some more series today. We are going to talk about those series that are specifically arithmetic series. So what happens when you take an arithmetic sequence and add up all of the terms? That is called an arithmetic series because the series is where you're adding those terms. So we'll put down, I'm using green today. An arithmetic series is simply the sum of an arithmetic sequence. Now, real important to note here, everything that we do today will be specifically for arithmetic series. So these formulas that we talk about today will not work for geometric sequences and series, and they won't work for the other series that, whether they be quadratic or more like Fibonacci-like sequences where you're adding the terms. This only works if there is a common difference as you move from one term to the next. So I'm going to flip my page over because I don't just want to give you the formula. I want us to see where it comes from. So I'm going to turn this over and look for just an extra example here. Let's take an arithmetic sequence. Let's say we have 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16. I'm going to stop right there and look at those 1, 2, 3, 4, 5, 6, 7, 8 terms. So we have 8 terms here that we're adding. Eight's not an excessively large number, so we could grab our calculator or we could just mentally add these numbers together. But this is in fact an arithmetic series because notice that there is a common difference of 2 as you move to the next term. We're adding 2 each time. What I'd like for us to look at, though, is a simpler way to add than just having to add 8 terms, to look for some patterns. So notice here, if I actually take this first term and connect it with the last term. If I look at adding the first and the last term, 2 plus 16 is 18. Well, look if I add the next 2 terms. Isn't 4 plus 14 also 18? And isn't 6 plus 12 also 18? And 8 plus 10 also 18. We're able to pair these terms from the top and the bottom, matching them up, and we get 18s. We have a sum of 18s. In fact, how many 18s do we have? We have 1, 2, 3, 4 18s. So I can think of this as 4 times 18, which 4 times 18 happens to be 72. And that's a fairly quick way to add that. I'm a little bit better at multiplying those numbers than I would be just adding all of those 8. But this also is going to help us because let's actually look and see, where did this 18 come from? That 18 came from adding these pairs of numbers. And the easiest way to show that would be it came from the first term and the last term, and we'll call that last term a sub n. Okay, where I'm adding n terms. And how many terms do we have? N is 8. We have 8 terms here. Well, how many 18s did I have? I had 4 of them. Well, how is that related to 8? It's half as many because I paired them up. So I have half as many pairs as I do the entire number of terms I'm adding. So another way to describe 4 would be n divided by 2. And this gives me the sum of those first 8 terms if n is 8. Well, right here, we've just derived our formula for the sum of an arithmetic series. And this actually originated back with a mathematician named Carl Friedrich Gauss. In the late 1700s, he came up with this in elementary school. Doesn't that make you feel clever? I'm just in amazement. His teacher decided he didn't really want to teach that day and wanted to give his students some busy work to keep them occupied so he didn't have to deal with them. And so he told all of his students that they needed to add the first 100 counting numbers. They needed to add the numbers from 1 to 100. And he was hoping, because obviously they didn't have calculators back in the late 1700s, that this would take a great deal of time. Well, little Carl came up with the answer quite quickly by doing this. He knew that there were some numbers in between, and then it would be 98 plus 99 plus 100, and he used that same thinking. There's 101, there's 101, there's 101, so there would be 101, and how many pairs? Well, it would be half as many as the number of digits, so there were 50 of them. And so he did that multiplication problem, and I believe that's 5,050. And he answered his teacher's question much more quickly than he expected. Did not, I don't know if it impressed the teacher or annoyed him, but that is where our sum formula comes from. Now, I like it in this form because it makes sense to me as we derive it. And so you'll see this from me just because it makes more sense to my brain, but I'll show you a couple other ways that you might see it in textbooks or in answer keys. No, this is not what I'm wanting to do. I just want that. There we go. N over 2 times the first term plus the nth term. I was getting into those other forms. Sometimes you'll see it like this. A sub 1 plus a sub n all over 2. You can see it like that. Or you could see it n times a sub 1 plus a sub n all over 2. Different forms, but I do like this one the best. N over 2 times the sum of the first and the last term. I just think that's the simplest. And that is where n is the number of terms. And a sub 1 is the first term. And a sub n is the last term that you're adding. Because we do know if we were doing an infinite number of terms, the series, an arithmetic series, either is going to go to positive infinity or negative infinity. So that's not quite as exciting. So there will be a last term. All right, let's take a look. We're not going to do all of these examples. I think we'll do the left-hand side here. Let's look here. We're trying to find the sum of the first 18. Well, that means we better figure out the first term and the 18th term, and then we'll be able to use our sum formula. So to find the 18th term, you could just keep adding. Notice this is arithmetic. Adding 3 each time. I think I'm going to write the explicit formula for it. Remember, that would be the common difference times n minus 1 plus that first term. And if I simplify that, that would be 3n plus 4. Some of you might have gone right there. Common difference times n plus the 0th term. Remember, what would be right before that would be a 4. Then I can use that to find the 18th term. 3 times 18 plus 4, that's going to give me 58. So I know the 18th term is 58. That first term is 7. I'm going to plug it into my formula. So the sum of the arithmetic sequence would be, let's see, n is 18, because I'm looking for the first 18 terms. So 18 divided by 2 times that first term plus the last term. That is actually 9 times 65, which is 585. And that's how our formula works. All right, how about number 3? Let's try that. We're looking for the sum of the first 21 terms. Again, I need to find that explicit formula. Let's see what we're adding each time. It actually is easier for me to see what we're adding here with these positive numbers. I'm adding 2.5, and then, oh yeah, I am adding 2.5. So this is going to be 2.5 n plus that 0th term. If I go 2.5 behind there, that's a negative 6.5. So that makes the 21st term 2.5 times 21 minus 6.5. And that, if I plug that into my calculator, gives me 46. All right, so that is the 21st term. So if I'm looking for the sum of the first 21 terms, now 21 is n over 2. Notice that's not going to be a nice whole number. That's okay. It just meant if I listed all of them out, that there would be a middle term that didn't have a buddy. It was a half of a sum. First term plus last term. And so if I put that into my calculator, 21 divided by 2, that of course is 10.5 times, oh, I need to do 10.5 times negative 4 plus 46, and I've got 441. All right. Now, when you see that sigma notation, remember that sigma notation, that's that big Greek letter sigma. Here I am trying to add the first 10 digits of 6k plus 1. Now you do need to stop and ask yourself, is this actually an arithmetic series? And how do we determine that? That is if our explicit formula is linear. If it's linear, it is arithmetic, and we can use our formula. If it's not linear, then I would actually have to plug in those k values and write them out, all 10 terms, and then add them. But since it is linear, it will be an arithmetic sequence. So I can just look for my first term. That would be if I plug in k as 1 there. So 6 times 1 plus 1 is 7. And then I'm going to look for my last term, which would be the 10th term, that number up top. If I plug in 10 for k, I get 6 times 10 is 60 plus 1 is 61. So now I have my first term. That series, the first term is 7 plus the last term. And I have 10 terms. And so the sum of 68, there will be 5 of them. 5 times 68 is 340. All right. That is the sum of an arithmetic series. Now let's see if we can actually put it into an application. By the way, notice all of these. I don't think we need to go through each of these. We might just chat about this one right here. Notice it starts with the 4th term. So our 4th term really in our formula would be the first term. And so that would be plugging in a 4 there. So that first term would be 20 minus 27, which would be negative 7. The 17th 14, plugging in a 17, that's actually going to be the 14th term. 17 minus 4 is 3, so they're 13, sorry, 17 minus 4 is 13. So there are actually, if we're going from 4 to 17, there are going to be 14 terms. So 5 times 17 minus 27, that's 58. So just be careful with that if we're not starting with 1 to a maximum that you have to figure out how many terms that there are. I'm not going to finish that one. I think you can probably do that, but take note on those. And our formula works for all of these because they're all linear. All right. Last one, number 12. Tickets for a concert opened up for sale online. The number of people that purchased tickets in each of the first 4 minutes is shown in the table at the left. If this pattern continues and the concert venue can hold a maximum of 75,000 people, find the number of tickets left after the first 2 hours. Okay, well, let's see what's going on with these ticket sales. Each minute that goes by, we are selling 8 more tickets. So our common difference is 8, which means that it is arithmetic. So if I write an explicit formula here, I know that my common difference is 8 times the number of minutes. That's what n will be. And then how many actually were in the 0th minute? Subtract 8, that would be 27. So a sub n is equal to 8n plus 27. So I'm really trying to figure out after the first 2 hours, how many tickets were sold after the first 2 hours. I have to add up how many tickets were sold each minute. It's increasing by 8 each minute. So in 2 hours, since this is in minutes, 2 hours is 120 minutes. So I'm really going to be looking where n is 120. So n over 2 times how many were in the first minute? Well, that was 35. And then how many are in the 120th minute? Well, let me figure that out. 8 times 120 plus 27. That is 987. So this total, 120 divided by 2 is 60, times the sum of 35 plus 987. That is 61,320. Now that is not my answer. That's how many were sold after the first 2 hours. But I want to find the number of tickets left. So there are 75,000 total tickets. And I will subtract the 61,320 that were sold. Whoops, not plus, minus the answer. And there are 13,680 tickets left. So take care in those applications. Make sure that you're actually answering the question that is being asked, but it should refer to an arithmetic series and that formula. So what you're going to work on tonight, I just want to show you the directions here. Homework 4, you are going to be having questions based off of last lesson's notes and then arithmetic series. So it's going to be very important that you only use the formula that we talked about today if in fact the series is arithmetic. If not, you're going to need to write out all of the terms and add them up just with a calculator or in your head. So notice on these here, not all of them are arithmetic, and it does actually ask you to expand. Okay, so follow the directions and enjoy homework 4. Email me any questions. Thank you.